Look up at the night sky on any clear evening, and you will see what every generation before you has seen. Points of light scattered across the dark, some bright enough to pierce city haze, others so faint you must wait for your eyes to adjust before they emerge. Each of those points is a sun. Many are larger than our own, hotter, older, younger, stranger. And between you and the nearest one, just the nearest, lies a gulf so vast that the numbers we use to describe it begin to lose their meaning. Proxima Centauri floats roughly 4 light-years from Earth. That sounds almost manageable until you remember what a light-year actually is. Light travels at 186,000 miles every second. In the time it took you to read that sentence, a beam of light crossed a distance greater than the circumference of Earth 7 times over. Now, let that beam run. Let it run for an entire year, racing through the vacuum at that impossible pace, never slowing, never tiring. The distance it covers in those 12 months is a single light year. Multiply that by 4, and you have the abyss between us and our closest stellar neighbour. If you launched a spacecraft today using the most powerful rocket humanity has ever built, pointed it directly at Proxima Centauri, and let it coast at the speeds we can actually achieve, you would not arrive for tens of thousands of years. Your great-great-grandchildren would be dust before the ship crossed even a meaningful fraction of that darkness. The stars, it seems, are not just far. They are locked away behind a wall that the laws of physics themselves appear to have built. For most of the 20th century, we believed that wall was absolute. Albert Einstein had shown, with mathematics elegant enough to make philosophers weep, that nothing carrying information, nothing with mass, nothing that could ever matter to anyone could outrun a beam of light. As you push an object faster and faster, time itself begins to slow for that object. Its mass swells, climbing toward infinity. The energy required to accelerate it even 1 more mile per hour rises without limit. At the speed of light, the equations break. They demand infinite energy. They demand that time freeze entirely. They demand the impossible, and the universe, so far as anyone could tell, always enforced its own rules. This was not a failure of engineering. It was not a problem we could solve with better rockets or cleverer fuels. It was a fundamental feature of reality, written into the geometry of space and time themselves. The cosmic speed limit was not a fence to be climbed. It was the shape of the playing field, and no matter how fast you ran, the field stretched on forever in every direction. And then, in a small corner of theoretical physics, someone noticed a loophole. If you would like to follow slow journeys like this one, consider tapping the like and subscribe buttons. They help others find these quiet explorations. Now let us begin. The year was 1994. Miguel Alcubierre was a young physicist from Mexico, finishing his doctoral work in Wales, surrounded by the grey skies and green hills of a country about as far from the deserts of his homeland as the stars themselves felt from any human hand. He was thinking about general relativity, that grand cathedral of thought Einstein had constructed 80 years earlier. And somewhere in the mathematics, he saw something that had been hiding in plain sight. Einstein's great insight had been that space and time are not separate things. They form a single fabric, a continuum, and that fabric is not rigid. Mass bends it. Energy warps it. The planets do not orbit the sun because some invisible force tugs at them. They orbit because the sun's mass has curved the space-time around it, and the planets are simply following the straightest possible paths through that curved landscape. Gravity, in Einstein's universe, is geometry. But if space-time can bend, Alcubierre reasoned, perhaps it can also stretch. Perhaps it can compress. Perhaps if you had the right kind of energy, you could squeeze the space in front of a ship and expand the space behind it, creating a wave in the fabric of reality itself. The ship would not move through space. It would sit still, perfectly motionless, inside a bubble of flat, calm geometry. But the bubble would surf forward on that wave of warped space-time, carried along as the universe itself rearranged around it. Inside the bubble, nothing would violate Einstein's laws. The ship would experience no acceleration. The crew would float in perfect stillness. They might sip coffee and watch the stars drift past and never feel a single tremor. But from the perspective of a distant observer, the bubble would be racing across the cosmos at speeds that made light itself look sluggish. Alcubierre wrote down the mathematics. He showed that such a bubble was, at least on paper, consistent with general relativity. The equations did not forbid it. The geometry was strange, exotic, but not impossible. He had found a way to move faster than light without ever breaking the speed limit, because the ship itself was not moving at all. Space was. He called it a warp drive. The name came from science fiction, from Star Trek and the voyages of the Enterprise. But the mathematics came from Einstein, and the implications were as serious as anything physics had ever produced. Picture what this means. Imagine you are standing on a long rubber sheet stretched tight between two poles. A toy car sits in the middle. Normally, to move the car from one end to the other, you would push it. It would roll across the rubber, covering distance in the ordinary way. But now imagine you could grab the rubber behind the car and stretch it, while simultaneously compressing the rubber in front of the car. The car itself does not move. It stays fixed on its little patch of rubber, but the patch of rubber it occupies is now much closer to the far pole than it was a moment ago. You have transported the car without the car ever travelling. This is what Alcubierre's warp bubble would do, not to rubber, but to space-time itself. The ship would ride a wave of compressed and expanded space, arriving at its destination not because it had crossed the distance, but because the distance had been rearranged around it. It is a beautiful idea. It is also, as Alcubierre himself immediately recognised, an idea that comes with a staggering price. To bend space-time in this way, to compress it ahead and expand it behind, you would need a kind of energy that no one has ever seen, measured, or held in their hands. You would need energy with negative density. Let that phrase settle for a moment. Negative energy. Not just a small amount of energy, not just an unusual form, but energy that weighs less than nothing. Energy that pushes outward where everything else in the universe pulls inward. Every piece of matter you have ever touched, every photon of light that has ever warmed your skin, every field and force and particle that makes up the cosmos as we know it, all of it has positive energy. It adds to the fabric. It curves space-time inward. It pulls. Negative energy, if it exists at all, would do the opposite. It would push space-time outward. It would create the expansion behind the bubble, the repulsion that lets the wave form in the first place. And in Alcubierre's original calculations, you would need an almost incomprehensible amount of it. The first estimates suggested that to create a warp bubble large enough to carry a modest spacecraft, you would need negative energy equivalent to the total mass energy of Jupiter. Not a little bit of exotic matter, not a thimbleful of some rare isotope, an entire giant planet, converted entirely into this hypothetical universe-bending substance. Later refinements brought the number down. Physicists sharpened the math, narrowed the bubble, optimized the geometry. Some estimates dropped the requirement to something closer to a few tons of negative energy. Others found ways to shape the bubble that reduced the cost still further. But even at its most optimistic, the requirement remained extraordinary. We do not know how to make negative energy. We do not know if it can exist in the quantities needed. We are not even certain the universe allows such a thing to persist outside the flickering quantum fluctuations of the vacuum. And yet the equations remain. The loophole persists. General relativity, the most successful theory of gravity ever devised, does not forbid the warp bubble. It merely demands a price we do not know how to pay. This is the tension at the heart of everything that follows. A door stands open in the laws of physics. Beyond it lies the galaxy, perhaps the universe, suddenly within reach. But the key to that door may not exist, or may exist only in forms so fleeting and fragile that no technology could ever grasp them. We are left staring at a possibility that is neither forbidden nor permitted, neither fantasy nor fact. We are left with a question that has haunted physicists for 3 decades. Is the warp drive a glimpse of humanity's future, or is it the cruelest mirage the universe has ever offered? To understand why this question matters, you must first understand how deeply the speed of light has shaped our vision of the cosmos. Every plan we have ever made for reaching the stars begins and ends with that barrier. Every science fiction story that sends humanity outward, every dream of colonizing distant worlds, every hope that our species might one day outlive this single fragile planet, all of it runs headlong into Einstein's wall. Consider the scales involved. The Milky Way galaxy, our home, stretches roughly 100,000 light-years from edge to edge. It contains somewhere between 100 billion and 400 billion stars, each with its own retinue of planets, moons, asteroids, comets. Many of those planets orbit in the habitable zones of their stars where liquid water could exist, where life as we know it might take hold. The sheer number of potentially living worlds in our galaxy alone is staggering. But we cannot reach them. Not in any time frame that matters to a human life, not with any technology we currently possess or can reasonably foresee. Even at the speed of light, a speed we have no way to achieve, crossing the galaxy would take 100,000 years. Our nearest neighbouring galaxy, Andromeda, lies 2.5 million light-years away. The observable universe spans 93 billion light-years. The numbers become absurd, distances so vast that they cease to feel like distances at all. They feel like walls. This is not merely a practical problem, it is an existential one. If the speed of light is an absolute limit, then the universe is not a neighbourhood. It is a collection of islands separated by uncrossable oceans. Life might flourish in 1 billion places, civilizations might rise and fall around 1 trillion stars, and none of them would ever meet. Each would be marooned, forever, on its own island of light. Some have accepted this fate with a kind of melancholy grace. The philosopher Enrico Fermi once asked why, if intelligent life is common, we have never seen evidence of it. One answer is simply that the distances are too great. Civilizations bloom and wither, but they never touch. The galaxy is not silent because it is empty. It is silent because no signal, no ship, no explorer can cross the void in time, but others have refused to accept this. They have searched for loopholes, for exceptions, for cracks in the wall. And Alcubierre's warp drive is the most famous crack of all. The physics of the warp bubble begins with a simple observation. General relativity tells us that space-time is dynamic. It is not a fixed backdrop against which events unfold. It is itself a participant in the drama, stretching, compressing and rippling in response to the matter and energy it contains. Black holes warp it so severely that light cannot escape. Gravitational waves send ripples across it at the speed of light, stretching and squeezing space as they pass. The expansion of the universe itself is nothing more than space being created, the fabric growing between galaxies, carrying them apart like raisins in a rising loaf of bread. Alcubierre realized that if space can expand and contract, then in principle it can do so in a controlled way. You could, if you had the right tools, create a region of contracted space and a region of expanded space, arranged in a specific configuration around a central bubble. The bubble would remain flat, calm, undisturbed. But the space around it would be bent in precisely the way needed to carry the bubble forward. The mathematics of this configuration are written in the language of general relativity, metrics and tensors, curvature and geodesics. Alcubierre constructed a metric, a description of the shape of space-time, that embodied this geometry. He showed that the metric satisfied Einstein's field equations, the fundamental laws governing how matter and energy curve space-time. The warp bubble was not a fantasy. It was a solution. It was as real, mathematically, as a black hole or a gravitational wave. But mathematics is not physics. A solution to the equations is not the same as a phenomenon that exists. Einstein's field equations are famously permissive. They admit solutions that describe rotating cylinders of infinite length, solutions that contain closed time-like curves, paths through space-time that loop back on themselves, allowing travel into the past. Not every solution corresponds to something the universe actually allows. The question is whether the warp bubble requires anything impossible, anything that violates the deeper rules of physics, and here the trouble begins. Because to create the warp bubble, you do not merely need energy. You need energy that behaves in a way no known energy behaves. You need negative energy density. In classical physics, energy is always positive. A ball rolling across a table has kinetic energy. A stretched spring has potential energy. A hot cup of coffee has thermal energy. All of these are positive. They add up. They contribute to the total mass of a system, because in Einstein's universe, mass and energy are two faces of the same coin. E equals mc squared. Energy has weight. Negative energy would have negative weight. It would repel rather than attract. It would violate the energy conditions, a set of assumptions that physicists use to ensure that space-time behaves sensibly. Without the energy conditions, you can build time machines, create traversable wormholes, make singularities naked. The energy conditions are the guardrails that keep general relativity from descending into chaos, and the warp bubble violates them. It requires space-time to curve in ways that demand energy of the wrong sign, energy that pulls space-time apart rather than pushing it together. This is not a minor technicality. It is the central challenge of the entire enterprise. Does negative energy exist? The answer, astonishingly, is perhaps. In quantum mechanics, the rules are stranger than classical physics admits. The vacuum of space is not truly empty. It seethes with fluctuations, particles and antiparticles flickering in and out of existence, fields rippling with zero-point energy. And in certain circumstances, quantum effects can produce regions where the energy density drops below zero. The most famous example is the Casimir effect. Place two uncharged metal plates very close together in a vacuum, and you will find that they attract each other. This attraction arises because the quantum fluctuations of the electromagnetic field are slightly different in the narrow gap between the plates than in the open space outside. The result is a small negative pressure, a region where the energy density is technically less than the vacuum average. It is not much. It is far too weak to bend space-time in any measurable way. But it exists. Negative energy in some sense is real. The question is whether it can be harnessed. Can we create large regions of negative energy? Can we sustain them? Can we shape them into the precise configuration needed for a warp bubble? The honest answer is that we do not know. The quantum effects that produce negative energy are fleeting and fragile. They arise in highly constrained circumstances and vanish the moment you try to scale them up. The amounts involved are minuscule, orders of magnitude below anything useful. Bridging the gap between a Casimir effect and a Jupiter's worth of negative energy is not merely difficult, it may be impossible. Some physicists have argued that the universe contains deep principles, not yet fully understood, that forbid the accumulation of negative energy in useful quantities. These are called quantum inequalities. They impose limits on how much negative energy can exist in a given region, and for how long. If the quantum inequalities are fundamental, then the warp bubble may be mathematically consistent but physically unreachable. It may be a mirage, a solution that the equations permit but that nature refuses to instantiate. Others remain more hopeful. They point out that our understanding of quantum gravity is incomplete. General relativity and quantum mechanics do not fit together neatly. They describe different regimes, different scales, and at their intersection, at the heart of black holes, at the first instant of the Big Bang, they produce contradictions and infinities that tell us something is missing. Perhaps in the full theory, the theory that unites relativity and quantum mechanics, negative energy behaves differently. Perhaps the principles that forbid warp bubbles in our current understanding are artifacts of our ignorance, rules that dissolve once we see the deeper structure. This is the landscape in which the warp drive lives. It is not forbidden. It is not permitted. It floats in a twilight zone between the possible and the impossible, waiting for someone to turn on the lights. But let us set aside for a moment the question of whether we can build a warp drive. Let us ask instead what it would mean if we could. Imagine a ship wrapped in a bubble of contracted and expanded space, surfing through the cosmos at effective speeds many times the speed of light. The crew inside feels nothing unusual. They experience normal gravity, normal time, normal physics. A cup of coffee sits motionless on the table. The stars through the window are strange. Relativity warps the light that reaches them, blue shifting the stars ahead, red shifting the stars behind, wrapping the sky into bizarre patterns. But otherwise the passage is calm. Outside the bubble, the universe rearranges itself. Space compresses ahead, stretches behind. Distances that would take millennia to cross at conventional speeds collapse into hours, days, weeks. The ship arrives at Proxima Centauri not after tens of thousands of years, but after an afternoon. Alpha Centauri, Tau Ceti, the swarm of stars within a few dozen light years, suddenly they are within reach, not for generation ships, not for frozen embryos, not for uploaded minds transmitted at light speed, for people, living, breathing, aging human beings who step off the ship and walk under an alien sun without having missed a single heartbeat of history back home. The implications cascade outward. If you can reach the nearest stars in hours, you can reach the far side of the galaxy in years. You can visit the great nebulae, the stellar nurseries where new suns are being born. You can approach the supermassive black hole at the galactic center, study its event horizon, map the space-time around it. You can travel to Andromeda, to the Magellanic Clouds. to galaxies so distant that their light has been travelling toward us since before Earth existed. The universe, for the first time in history, becomes navigable, and with navigation comes something else: connection. If faster than light travel is possible, then the isolation that seemed baked into the cosmos dissolves. Civilizations separated by thousands of light years could trade, communicate, meet. The galaxy transforms from a scattering of unreachable islands into a single continuous territory, a place where history can happen on a scale larger than any planet, any star system, any individual culture. This is the dream that has animated physics since Alcubierre published his paper. It is not merely a technical dream, a puzzle to be solved for its own sake. It is a dream about what humanity could become, about the shape of our future, about whether we are destined to remain on this single fragile world or whether the stars might one day be ours. But dreams do not build starships. Mathematics does not create bubbles of warped space-time, and the path from Alcubierre's equations to anything resembling a working drive is paved with obstacles that may prove insurmountable. The negative energy problem is only the beginning. Even if you could generate the exotic matter needed, you would face questions of engineering that dwarf anything humanity has ever attempted. How do you shape the bubble? How do you control it? How do you stop? The mathematics of the warp drive in its original form offers no mechanism for starting or stopping the journey. The bubble, once formed, would presumably carry you forward forever, unable to break, unable to steer, a prisoner of your own success. Later researchers have proposed solutions. Perhaps you could adjust the geometry of the bubble on the fly, creating symmetries that allow acceleration, deceleration, turning. Perhaps you could design the field generators to be controllable, dialing the warp factor up and down as needed. But these proposals remain speculative. No one has built a prototype. No one has tested a single component. The warp drive remains a thought experiment, a mathematical possibility, a vision of what might be done if every other problem was somehow solved. And there are deeper concerns still. Some physicists have argued that the warp bubble, if it could be created, would generate a wall of radiation at its leading edge. As the bubble moves, particles from the cosmic microwave background, from interstellar gas, from every source of ambient radiation, would pile up at the compressed region of space ahead. When the bubble stops, that radiation would be released in a catastrophic burst, a blast potentially powerful enough to sterilize any planet in the ship's path. You would arrive at your destination not as an explorer but as a destroyer, your means of travel transformed into a weapon of annihilation. Others have questioned whether the bubble could form at all. The creation of the warp field might require conditions inside the bubble that cannot be sustained by any physical process. The mathematics might describe a solution that exists only on paper, a shape that space-time could hold in principle, but could never be coaxed into in practice. These are not objections that can be easily dismissed. They arise from the same equations that make the warp bubble possible in the first place. So where does this leave us? It leaves us, honestly, in a state of suspended wonder. The warp drive is not impossible. It is not ruled out by any known law of physics. The equations that permit it are the same equations that describe black holes, gravitational waves, the expansion of the universe. General relativity does not forbid travelling faster than light. So long as you never actually exceed the local speed limit, so long as it is space doing the moving and not you. But the price remains negative energy in quantities we have no idea how to produce. Engineering challenges so far beyond our current capabilities that they barely register as engineering at all. Theoretical concerns about radiation, about stability, about the very possibility of creating and controlling such a bubble. The loophole is real. The question is whether we will ever be able to walk through it. And perhaps that is the point. Perhaps the warp drive is not a blueprint but a beacon. It tells us that the universe, for all its vastness, for all its terrifying indifference, does not absolutely forbid what we most desire. The laws of physics, as we understand them, leave a door ajar. It may be a door we never manage to open. It may be a door that leads nowhere we can reach, but it is there. It is part of the structure of reality, and that matters. Because as long as the door remains, so does the dream. The dream of ships sailing between the stars, the dream of civilization spanning the galaxy, the dream of human beings standing on worlds so distant that our sun is just another point of light in an unfamiliar sky. These dreams may never become real, but they are not, by the laws of physics, impossible, and that distinction between the impossible and the merely unachieved is perhaps the most important distinction there is. So let us look more closely at the landscape. Let us examine the physics of negative energy, the experiments that probe its limits, the theorists who have spent their careers searching for ways to make the warp bubble work. Let us ask what we know, what we do not know, and what we might one day discover. Because somewhere in that question, in that gap between Einstein's equations and the engineering of starships, lies the shape of humanity's future. And whatever that shape turns out to be, it begins here, with a loophole noticed by a young physicist in Wales 3 decades ago, staring at the mathematics of bending space. The sky is full of islands. The ocean between them seems uncrossable, but the fabric of the ocean itself, the very nature of distance, may not be what it appears. And if we can learn to move the ocean rather than sailing through it, then perhaps, just perhaps, the islands are not as far apart as they seem. Rest with that thought for a moment. Let the scale of it settle. The nearest stars are impossibly far. The galaxy is a vast and lonely place, but there is a loophole in the laws, a crack in the wall, a whisper of a possibility that distance itself might be negotiable, and we have only just begun to listen. The whisper begins with a peculiar substance, or rather, with the absence of substance as we normally understand it. To bend space in the way Alcubierre described, to contract the fabric ahead and stretch it behind, the equations demand something that behaves in a manner profoundly opposite to ordinary matter. They demand energy that is, in a very precise mathematical sense, less than nothing. This is not a metaphor. It is not a poetic flourish. When physicists speak of negative energy, they mean exactly what the words suggest. A region of space where the energy density drops below the vacuum, below the baseline of emptiness itself. Think of it this way. Imagine a still pond. The surface of the water represents the energy of empty space, not zero, but a particular level, a kind of floor. Ordinary matter and radiation are like ripples on that pond, disturbances that rise above the baseline. Negative energy would be a trough that sinks below the surface, a dip in the fabric of reality itself, a region where there is less than nothing. Your intuition rebels. How can there be less than nothing? If you remove all the air from a chamber, you have a vacuum. What could possibly lie beneath a vacuum? And yet the mathematics of quantum field theory, the same mathematics that predicted antimatter and the Higgs boson, and the precise magnetic moment of the electron to 12 decimal places, suggest that such troughs are not only possible but inevitable under certain circumstances. The question is not whether negative energy exists. The question is how much of it you can gather, how long you can hold it, and whether you can shape it into the configurations that a warp drive would require. Let us step into the quantum world for a moment. It is a place where emptiness is never truly empty. Even in a perfect vacuum, stripped of every particle and every photon, the fabric of space seethes with activity. Fields flicker in and out of existence. Virtual particles, pairs of matter and antimatter, bubble up from nothing, exist for the briefest instant, and annihilate each other before they can be observed. This is not speculation, it is measured fact. The vacuum is not a void but a restless sea, and its energy, though it averages to a particular baseline, fluctuates wildly at very small scales. In 1948, a Dutch physicist named Hendrik Casimir noticed something strange about these fluctuations. If you take 2 perfectly flat metal plates and bring them very close together, close enough that the gap between them is measured in nanometers, in billionths of a meter, something unexpected happens. The plates are pushed together by an invisible force, not gravity, not electromagnetism in the ordinary sense, but something subtler, the pressure of the vacuum itself. Here is why. The quantum fluctuations of empty space create virtual photons of every possible wavelength. Outside the plates, in the open vacuum, all wavelengths are allowed, but between the plates, only certain wavelengths fit. Imagine the gap as a tiny box. Only waves that match the dimensions of the box can exist inside it. Waves that are too long, that do not fit between the walls, are excluded. This means there are more fluctuations pressing on the plates from outside than from between them. The imbalance creates a force. The plates are squeezed together. This is the Casimir effect. It has been measured in laboratories around the world. It is real, repeatable, and exquisitely precise. And here is the crucial point. Between those plates, in that narrow gap where certain fluctuations are excluded, the energy density of the vacuum is lower than it is outside. Lower than the baseline, lower than nothing. Between the plates, for just a sliver of space, negative energy exists. Let that settle. This is not theory waiting to be confirmed. This is experimental physics. The Casimir effect tells us that nature permits regions where the energy density drops below the vacuum, where the fabric of space-time is, in some sense, pulled inward rather than pushed outward. The exotic ingredient that Alcubierre's equations demand has been measured. It has been held, however briefly, in the gap between two metal plates in a physics laboratory. But there is a distance, a vast and perhaps unbridgeable distance, between the whisper of negative energy in a Casimir experiment and the roaring ocean of it that a warp drive would require. In Alcubierre's original calculation, the amount of negative energy needed to sustain a warp bubble was staggering. He estimated that you would need a quantity of this exotic substance, equivalent in magnitude to the mass energy of a planet. Not a small planet, Jupiter, perhaps more. And not positive energy, not the kind you could gather from fusion reactors or antimatter annihilation, but negative energy pulled somehow from the quantum vacuum and shaped into a shell around your ship. Later researchers refined the numbers. Some found ways to reduce the requirement, by optimizing the shape of the bubble, by making the walls of the warp field thinner and more sharply defined. They brought the energy budget down from planetary to merely astronomical. One estimate suggested that with careful tuning, you might need only the mass energy of a few hundred kilograms of matter, converted entirely into negative energy. That sounds almost manageable until you remember that we have no idea how to produce negative energy in bulk, no idea how to store it, no idea how to shape it into the precise configurations the equations demand. The Casimir effect gives us a glimpse, a proof of principle, but the energy it provides is vanishingly small. The force between two plates a micrometer apart is measured in micronewtons. The negative energy density between them is a whisper, a flicker, a shadow on the wall of a cave. To build a warp drive, you would need not a shadow but a searchlight, not a whisper but a shout loud enough to bend the cosmos, and there are deeper problems still. Quantum field theory, the framework that predicts the Casimir effect, also imposes limits on how negative energy can behave. These limits are called quantum inequalities, and they are not gentle suggestions. They are mathematical constraints woven into the structure of the theory itself. The quantum inequalities say, in essence, that you cannot borrow too much energy from the vacuum for too long. If you create a region of negative energy, the universe will demand that positive energy appear nearby to compensate. The deeper the trough, the more fleeting it must be. The longer you try to hold it, the shallower it becomes. Nature permits negative energy, but it does not permit a permanent debt. Every deficit must be balanced, every dip must be followed by a rise, and the product of depth and duration is constrained by fundamental constants. For a warp drive, this presents an almost insurmountable challenge. The bubble must persist for the duration of the journey. It must be stable. It must hold its shape as the ship travels, perhaps for days or weeks or years. But the quantum inequalities suggest that the kind of negative energy configurations needed for such a bubble may be inherently unstable, prone to collapse or dissipation the moment they are formed. Some researchers have searched for loopholes within the loophole. Perhaps they suggest there are exotic states of matter or energy that evade the quantum inequalities. Perhaps in extreme conditions, near the event horizon of a black hole, in the first instance after the Big Bang, in the heart of a collapsing star, the rules bend in ways we have not yet understood. Perhaps string theory or loop quantum gravity or some other framework beyond our current physics will reveal new possibilities, new ways to accumulate and stabilize the exotic substance the warp drive demands. But these are hopes, not proofs. As of now, as of this moment when we are speaking, the quantum inequalities stand. They do not forbid negative energy. They do not forbid the Casimir effect or the other fleeting glimpses we have caught of this strange substance. But they seem to forbid the bulk accumulation and long-term stability that a working warp drive would require. Let me try once more to give you a feel for what we are discussing. Imagine you are standing at the edge of a frozen lake in winter. The ice is solid, thick, reliable. You can walk across it. You can drive a car across it. It holds your weight without complaint. This is ordinary space-time, the fabric of reality as we experience it every day. Now imagine that somewhere beneath the ice, in the dark water below, there are currents. Occasionally, very occasionally, a bubble rises to the surface, and for an instant the ice grows thin, almost yielding, before freezing solid again. This is the Casimir effect, the momentary dip into negative energy that quantum mechanics permits. What the warp drive asks for is something far more ambitious. It asks for a hole in the ice, not a temporary thinning, but a permanent opening, a region where the frozen surface gives way to liquid possibility, where the normal rules no longer apply. And not just any opening, but one that can be shaped and moved, carried along as you travel, held open against the natural tendency of the ice to freeze solid once more. The equations say such an opening is possible. The quantum inequalities say the ice wants very badly to refreeze, and we do not yet know which constraint is stronger. There is another thread woven through this tapestry, another challenge that emerges from the mathematics itself. It concerns not just the creation of the warp bubble, but its consequences, the strange and perhaps dangerous phenomena that such a bubble might produce. In 2012, a group of physicists led by Stefano Finazzi and Stefano Liberati examined what would happen at the boundaries of an Alcubierre bubble. Their findings were troubling. As the bubble moves through space, it sweeps up particles from the quantum vacuum. These particles, accelerated by the intense curvature at the bubble's edge, accumulate energy. The faster the bubble moves, the more energy they gain. And when the bubble finally stops, when the journey ends and the warp field collapses, all that accumulated energy is released. The result, they calculated, would be catastrophic. A burst of radiation so intense that it would vaporize anything ahead of the ship. The destination would be annihilated by the arrival. The warp drive, in this analysis, is not just a transportation device, but a weapon. Perhaps the most destructive weapon imaginable, converting the journey itself into an extinction-level event at the point of arrival. This is not a flaw in the design. It emerges directly from the physics, the very mechanism that allows the bubble to move faster than light, the contraction of space ahead, the expansion behind, creates conditions at the boundary that trap and amplify quantum fluctuations. The bubble becomes a collector, a lens, focusing the energy of empty space into a beam of destruction. Other researchers have questioned these conclusions. Some have suggested that the radiation problem might be mitigated by different bubble geometries, by gentler accelerations, by clever manipulation of the field at the edges. The debate continues, but the possibility remains that even if we could build a warp drive, even if we could gather the negative energy and shape the bubble and overcome the quantum inequalities, the act of using it might be inherently catastrophic. Picture it. A ship emerges from warp at the edge of a solar system, carrying explorers from a distant world, and in the instant of its arrival, the accumulated energy of its journey blazes outward, a pulse of radiation brighter than a supernova, scouring the planets ahead of any possibility of life. The first contact between civilizations becomes, inevitably, the last. This is one of the dark threads in the mathematics. It may not be the final word. Physics advances, solutions are found. But it is a reminder that the universe does not give up its secrets without cost, that every loophole comes with conditions, every shortcut with caveats written in the language of energy and entropy and the deep structure of the vacuum, and yet researchers continue to search. The dream is too powerful to abandon. The equations are too tantalizing to ignore. In 2021, a new voice entered the conversation. Eric Lentz, a physicist at the University of Göttingen, published a paper that sent a small ripple through the community. He had found something unexpected. He had discovered a class of warp drive solutions that did not require negative energy at all. This sounds like a revolution. It sounds like the breakthrough everyone had been waiting for. But the details, as always, are complicated. Lentz's solutions do use only positive energy, only the kind of matter and radiation we know how to produce. But they require that energy to be arranged in very particular configurations, in shapes and densities that are far beyond our current engineering capabilities. The total energy needed remains enormous, not quite planetary, but still staggering, still vastly beyond anything we have ever concentrated in a single place. And there are questions about whether his solutions truly permit superluminal travel, whether the configurations he describes are stable, whether they can be created and controlled in practice. The warp drive community is cautious, hopeful but skeptical, waiting for further analysis, for other researchers to test his equations and find their limits. But Lentz's work represents something important regardless of its ultimate fate. It represents the possibility that the landscape of solutions is larger than we thought, that the original Alcubierre metric, with its demand for negative energy, is not the only path, that there may be other shapes the bubble could take, other ways to bend space, other configurations that thread between the constraints. This is how physics advances, not in sudden leaps but in the slow accumulation of possibilities. Each paper narrows the space of the impossible. Each calculation reveals new features of the terrain. The warp drive remains far beyond our reach, but the map of how to reach it grows more detailed with every passing year. There is a laboratory in the United States tucked away in a corner of the Johnson Space Center in Houston, where a small team has been quietly testing the edges of possibility. It is called Eagle Works, and its mission is to investigate propulsion concepts that mainstream physics considers unlikely or even impossible. In 2014, EagleWorks made headlines with a claim that startled the physics community. They reported measuring a small but persistent thrust from a device called the M drive, a closed cavity that appeared to produce propulsion without any exhaust, without any reaction mass, in apparent violation of Newton's third law. The scientific community was skeptical, deeply skeptical, and subsequent investigations by other groups failed to replicate the results. The M drive has largely faded from serious consideration. But EagleWorks also turned its attention to the warp drive, not to building one, that remains fantasy, but to testing whether the effects predicted by Alcubierre's equations could be detected at microscopic scales. The idea was simple in principle, fiendishly difficult in practice. If you could create even a tiny distortion in spacetime, a minuscule contraction or expansion, your instruments might be able to measure it. The results have been inconclusive. The effects, if they exist, are far below the noise floor of current experiments, but the effort continues. There is something admirable about it, something deeply human. The willingness to test, to measure, to push at the boundaries even when the odds are long and the community is skeptical. This is how knowledge grows, not by declaring what is impossible, but by measuring carefully and honestly what is true. And perhaps that is the deeper lesson of the warp drive. Not that we will build one tomorrow, or in a century, or ever, but that the universe permits us to ask the question. The equations exist, the mathematics is consistent, the loophole is real, and as long as it remains real, as long as the door stays ajar, researchers will continue to probe its edges, to test its limits, to search for the key that might one day open it wide. The stars remain impossibly far. The ocean of space stretches out in every direction, vaster than intuition can grasp. But somewhere in the quantum vacuum, in the fleeting dips and troughs of the Casimir effect, in the strange mathematics of curved space-time, there is a whisper that says distance may not be what it seems, that the fabric of the cosmos might be bent as well as crossed, that the wall between the stars, for all its apparent solidity, might have a door we have not yet learned to see, and we are listening. The listening has a shape. It is patient and methodical, and often disappointing, but it is listening nonetheless. And to understand what we might one day hear, we need to step back from the bubble itself and consider the fabric it would move through, the space-time that would ripple and bend, the medium that makes the whole idea possible. Einstein gave us this medium. Before him, space was a stage and time was the ticking clock in the wings, both fixed, both unchanging, both indifferent to the drama unfolding within them. Newton had assumed as much. The universe was a vast emptiness through which objects moved according to predictable laws, but the emptiness itself was inert. It did nothing. It had no properties. It simply was. Einstein shattered that picture. In his hands, space and time merged into a single four-dimensional tapestry, and that tapestry was not passive. It curved in response to mass and energy. It told matter how to move. Planets did not orbit the sun because of an invisible force reaching across the void. They orbited because the sun's mass dimpled the fabric of space-time, creating a valley that the planets rolled around like marbles circling a drain. Gravity was not a force at all. Gravity was geometry. This is difficult to picture. We are creatures of three spatial dimensions, evolved to navigate savannas and forests, to judge distances and dodge predators, Our brains are not built to visualize four-dimensional curvature, but the mathematics is clear. Every mass, every concentration of energy warps the geometry of the cosmos around it. And that geometry determines how everything else moves. The sun curves space. The earth curves space. You curve space, though by an amount so infinitesimal that no instrument could ever detect it. And light, moving through this curved landscape, follows the contours. It bends around massive objects. It takes longer to cross regions where gravity is strong. This is not metaphor. This is measurement. The global positioning system satellites orbiting the Earth must account for the curvature of space-time to give you accurate directions. Without Einstein's corrections, your phone would drift by kilometers within a day. So space-time bends, space-time stretches, space-time responds to the energy within it. And if it can bend in response to a star, why not in response to something else? Why not in response to something we deliberately create? This is where the warp drive enters. Alcubierre's bubble is not magic. It is applied geometry. You take the equations Einstein gave us, the equations that describe how energy and momentum curve space-time, and you ask, what configuration of energy would produce the curvature we want? What distribution would contract space ahead of a ship and expand it behind? The answer, when Alcubierre worked it through, was the metric that bears his name. A precise mathematical description of a bubble of flat space, cocooned within a shell of curved space, moving through the cosmos while everything inside it remains still. The mathematics is beautiful. It is also ruthless, because the equations do not merely describe how the bubble would behave, they also prescribe what you would need to create it. And what you would need is something that, as far as we know, does not exist in any form we can gather and control. Negative energy density. The words sound almost innocent. Energy is usually positive. The heat in your coffee, the motion of your car, the light streaming from the sun, all positive contributions to the energy budget of the universe. But the equations of general relativity are agnostic. They describe how space-time curves in response to energy, and they are perfectly happy with energy that is negative. If positive energy creates gravity, negative energy creates anti-gravity. If positive energy pulls the fabric inward, negative energy pushes it outward, and the warp bubble needs both. It needs ordinary space-time curvature in some regions, and exotic repulsive curvature in others, layered together in a precise geometry that no natural process is known to produce. Where would this negative energy come from? This is the question that has haunted the warp drive since the moment Alcubierre published his paper, and the answer, such as it is, leads us down into one of the strangest basements of modern physics, the quantum vacuum. Say those words slowly and let them settle. The vacuum of space is not empty. We have touched on this before in the flickering virtual particles of the Casimir effect, but the full picture is stranger still. According to quantum field theory, every point in space is alive with fields. The electromagnetic field, the electron field, the fields for quarks and gluons and neutrinos and everything else that makes up the zoo of particle physics. These fields never rest. Even in their ground state, their lowest possible energy, they still fluctuate. They jitter and tremble and vibrate at every point in the universe, producing a faint, omnipresent hum of activity. This is not poetic license. This is observed physics. The Lamb shift, a tiny correction to the energy levels of hydrogen atoms, is caused by these vacuum fluctuations. The anomalous magnetic moment of the electron measured to extraordinary precision depends on them. The virtual particles that appear between Casimir plates are borrowing energy from this same sea of fluctuations, paying it back so quickly that the universe's accounts balance. The vacuum is not nothing. The vacuum is the most something that nothing has ever been. And here is the tantalizing part. The Casimir effect in certain configurations produces regions of space where the energy density is lower than the ambient vacuum, lower than zero in a certain sense. The virtual particles between the plates are restricted, their wavelengths constrained by the geometry, and so the energy density there is less than the energy density outside. This is not quite negative energy in the sense the warp drive needs, but it is a signpost, a hint that the quantum vacuum can, under the right conditions, be manipulated, pushed below its ground state, made to behave in ways that classical physics would forbid. The distances involved are heartbreaking. The Casimir effect is measurable only at separations of micrometers or less. The energy densities involved are tiny, almost absurdly tiny compared to what a warp bubble would demand. Scaling up from Casimir plates to a starship-sized bubble is not like scaling up from a candle to a bonfire. It is like scaling up from the weight of a single photon to the mass of Jupiter. The gap is not merely large. The gap is the kind of large that makes physicists use words like speculative and highly preliminary, and not currently achievable by any known means. But the gap is not infinite, and that matters. Consider where we were a century ago. In 1925, quantum mechanics was being born. Heisenberg had just formulated his matrix mechanics. Schrödinger would soon write his wave equation. The electron had been discovered less than 30 years before. The neutron was still undiscovered, the positron unobserved, the structure of the atom barely understood. If you had told a physicist of that era that within a human lifetime we would build machines that split atomic nuclei to release the energy of stars, they would have been skeptical. If you had told them we would one day manipulate individual atoms with scanning tunneling microscopes, position them one by one on a surface like pieces on a game board, they would have thought you were dreaming. The history of physics is a history of the impossible becoming merely difficult, and the difficult becoming routine. This is not a guarantee. Plenty of impossible things stay impossible, but it is a pattern worth noting. The boundaries of what we can do have expanded relentlessly, pushed outward by generations of researchers asking questions that seemed absurd until the answers arrived. So when we speak of the energy requirements of a warp drive, we must hold two thoughts in our minds at once. The first is that those requirements, as currently understood, are vastly beyond anything we can produce or control. The second is that our understanding is incomplete, our knowledge is growing, and the landscape of solutions may be larger than we have yet mapped. Let us talk about that landscape for a moment, about the modifications and variations and alternative approaches that have sprouted around Alcubierre's original idea like vines around a trellis. The first modification came from Alcubierre himself, working with other researchers to refine his original equations. The early estimates for the energy required were staggering, equivalent to the mass of Jupiter converted entirely into exotic matter, or more. But those estimates assumed a particular bubble geometry, a particular thickness for the warped region, a particular configuration. Other configurations required less, much less in some cases. By shaping the bubble more carefully, by making the warped region thinner and more efficient, the energy requirements could be reduced by orders of magnitude. Still enormous, still far beyond current capability, but no longer quite so absurd. Then came other researchers with other ideas. What if the bubble did not need to maintain a constant shape? What if it could pulse, expanding and contracting in a rhythm that reduced the peak energy demands? What if the geometry could be optimized for specific velocities, specific distances, specific missions? Each variation opened new possibilities and closed others. Each calculation revealed new features of the terrain. The soliton work we discussed earlier, the discovery that certain shapes might be achievable with positive energy alone, is part of this same exploration. So are studies of how the bubble would interact with the matter it encountered, with the radiation that fills interstellar space, with the cosmic microwave background that bathes the universe in ancient light. Each question leads to more questions. Each answer reveals new ignorance. This is the nature of physics at the frontier. You do not leap from impossibility to achievement in a single bound. You crawl forward, paper by paper, calculation by calculation, mapping the terrain. And sometimes, when you look back, you realize you have covered more ground than you thought. There is another thread to this story, one that does not lead directly to the warp drive but illuminates the same territory. It is the story of gravitational waves, those ripples in space-time that Einstein predicted in 1916 and that we finally detected almost exactly a century later. Einstein was not certain they existed. His equation suggested that accelerating masses should shake the fabric of space-time, sending ripples outward at the speed of light. But the effect was so weak, so impossibly subtle, that he doubted it could ever be observed. The mathematics was clear. The measurements seemed forever beyond reach, and yet. In September 2015, the LIGO detectors in Louisiana and Washington state recorded a faint chirp, a signal that rose in frequency over a fraction of a second and then fell silent. It was the sound of two black holes, each 30 times the mass of the Sun, spiraling together and colliding 1 billion light-years away. The collision had shaken space-time so violently that the ripples reached Earth, still detectable after crossing 1 billion years of void. How small was the signal? The mirrors in the LIGO detectors moved by less than 1,000th the diameter of a proton. The measurement was so delicate, so precise, that thermal vibrations in the mirrors themselves were a significant source of noise. A passing truck miles away could obscure the signal. A wave on the shore of a distant ocean could disturb the data. And yet, the detection happened. The signal was pulled from the noise. The ripples in space-time, predicted a century before, became part of the observed universe. What does this have to do with the warp drive? Nothing directly. We are not going to power a starship with gravitational waves. But the story illustrates something important about the arc of physics, about the relationship between theoretical prediction and experimental capability. Einstein doubted we could ever detect these waves. 100 years later, we detect them routinely. We have built a new kind of astronomy around them. We have observed neutron stars colliding, black holes merging, cataclysms that were invisible to every telescope that came before. The lesson is not that all predictions will eventually be confirmed. Many will not. Many ideas that seemed plausible have been ruled out by experiment, and that is how science should work. But the lesson is that capability grows, instruments improve, new technologies emerge that change what is measurable, and predictions that once seemed impossible to test become, eventually, possible. Hold that thought as we return to the warp drive, not as a promise that we will build one, but as a reminder that the landscape of the possible is not fixed. It shifts beneath our feet as knowledge accumulates. Now let us consider a question we've been circling around, approaching from different angles, not quite naming. What would it feel like? What would it mean to be inside that bubble if the bubble could somehow be created? You stand on the deck of a ship. The bubble forms around you, a shell of distorted space-time separating you from the cosmos outside. Within the bubble, space-time is flat, perfectly ordinary. The laws of physics work exactly as they always have. You can walk across the deck. You can pour a glass of water. You can watch the stars through a window. Nothing inside the bubble exceeds the speed of light. Nothing inside violates any law. But outside, the universe is moving. Space is contracting ahead of you and expanding behind you. Galaxies are streaming past at impossible velocities, not because they are moving, but because the distance between you and them is shrinking. You are still. The cosmos runs. How fast could you travel? The mathematics places no upper limit. At multiples of the speed of light, stars that take thousands of years to reach by conventional travel would slip past in months or weeks or days. The galaxy itself, 100,000 light-years across, could be traversed in a human lifetime. The wall between the stars would fall. The ocean of dark that isolates every island of light would become navigable. This is the dream that keeps researchers returning to the equations. Not the mathematics itself, beautiful as it is, but the promise beneath it. The promise that the cosmos might not be as lonely as it seems, that the vast emptiness might be crossable, that we might one day reach the distant shores. But the dream carries shadows, and those shadows too must be examined. Consider what happens when the bubble stops. The mathematics here is less developed, more contentious, but some analyses suggest a troubling possibility. As the bubble travels, it sweeps up the particles and radiation that fill interstellar space, accumulating them at its leading edge. When the bubble decelerates, when the distortion relaxes, that accumulated energy must go somewhere. Some calculations suggest it would be released in a concentrated burst, a pulse of radiation that could be lethal to anything in its path. The numbers are uncertain, the models make simplifying assumptions, but the possibility is there, lurking in the equations. A warp drive might arrive at its destination trailing destruction. The very act of stopping could sterilize the world you came to visit. There are potential solutions. Perhaps the bubble could be designed to dissipate gradually, bleeding off the accumulated energy over a longer time. Perhaps the arrival could happen at a safe distance, the ship completing its journey by conventional means. Perhaps the entire effect is an artifact of the simplified models, something that a more complete analysis would resolve. These are open questions. They are part of the terrain that remains to be mapped. There is another shadow, one that touches not physics but philosophy. If the warp drive is possible, why have we not seen it? The universe is ancient. Stars have been burning for billions of years, long enough for countless civilizations to rise and fall. long enough for technology to develop far beyond anything we can imagine. If faster than light travel is achievable even in principle, then older civilizations would have achieved it long ago. They would have crossed the galaxy. They would have left traces. They would perhaps have visited us. This is a familiar argument, a variation on the Fermi paradox. It proves nothing. Perhaps civilizations are rare. Perhaps they destroy themselves before they reach the stars. Perhaps they are here and we cannot recognize them. Perhaps faster than light travel is possible, but so difficult that even ancient civilizations have not mastered it. The silence of the cosmos is a mystery with many possible explanations. But the question lingers. It is part of the landscape we are mapping, one more feature of the terrain that must eventually be understood. And still the research continues. Still the papers appear in the journals, each one adding a detail, correcting an error, exploring a new corner of possibility. The warp drive community is small, often dismissed by the mainstream, sometimes mocked. But they persist, they calculate, they measure when measurement is possible. They keep the question alive. There is something admirable in this, something deeply human. The willingness to chase an idea that most consider fantasy, to spend careers on a possibility that may never become reality. It is the same impulse that sent the first ships across unknown oceans, that launched rockets toward the moon, that built the instruments to hear gravitational waves. The refusal to accept that the boundaries are fixed, the insistence that we can push further. Whether the warp drive will ever leave the realm of mathematics and enter the realm of engineering is a question without an answer. The obstacles are immense. The energy requirements remain daunting. The exotic matter remains hypothetical. The shadows, the questions about safety and feasibility, remain unresolved. But the equations exist. The loophole is real, and as long as it remains real, there will be those who study it, who probe its edges, who search for the key that might transform speculation into possibility. The stars remain impossibly far. They burn in their ancient solitude, separated from us by distances that mock our fastest ships. But the fabric of space-time, the very medium that defines those distances, may hold within it a secret, a fold, a bend, a way through that does not require crossing the void but only reshaping it. And somewhere, in quiet laboratories and cluttered offices, researchers are still searching for that shape. The bubble floats in their calculations, fragile, hypothetical, demanding something we have never found. But real in the only way that matters for now, real in the mathematics, real in the possibility. And possibility in physics is where everything begins. The bubble floats in possibility, and possibility for now is all we have. But let us slow down. Let us return to the heart of this strange dream and ask a simpler question. What would it actually feel like to ride inside a warp bubble? What would the crew experience as space itself carried them across the gulf between stars? Picture a vessel, not the sleek dart of science fiction, not the angular warship bristling with weapons, but something more modest. A cylinder, perhaps, or a sphere. Something that can fit entirely within the calm centre of the distortion, the eye of the storm where space remains flat and ordinary, and the laws of physics behave exactly as they do on Earth. Inside this vessel, gravity feels normal. Time flows at the expected rate. The crew floats or walks or sleeps, depending on how the ship is designed. They feel no acceleration. They feel no motion at all. And this is the strange, almost eerie truth of the warp drive. You would not know you were travelling. There would be no rush of velocity, no pressure pushing you back into your seat, no sense of the vast distances being devoured. Inside the bubble, you would simply exist, suspended in stillness, while the universe rearranged itself around you. Look out the window and you would see something unprecedented. The stars ahead would not streak into lines as they do in the films. They would shift, distort, compressed into a narrowing circle of light as space contracted before you. Behind, the stars would stretch, reddening, fading, as space expanded in the vessel's wake. You would be watching the geometry of the cosmos bend in real time, a visible testament to the distortion carrying you forward. Some calculations suggest the view would be haunting. A ring of compressed light ahead, an emptying darkness behind, and around you a strange halo where the bending of space lends distant objects into arcs and smears. You would be looking at the universe through a curved lens of your own making, a lens shaped not from glass but from the fabric of reality itself. And how fast would you travel? The mathematics allows in principle any speed, 10 times light, 100 times, 1,000. The equations place no upper limit on how tightly space can be contracted, how rapidly the bubble can surf across the cosmos. In the most optimistic scenarios, a journey to Alpha Centauri, our nearest stellar neighbour, could take weeks, days even. A voyage that would require 40,000 years at the speed of our fastest probes could be compressed into something a human life could contain. A journey that could be remembered. A journey from which you could return. But here is where the dream begins to fray at the edges. The faster you wish to travel, the more extreme the distortion must become. And the more extreme the distortion, the more exotic matter you require. The relationship is not gentle, it is steep, unforgiving, a curve that climbs toward quantities that strain the imagination. Early calculations, the ones Alcubierre himself performed, suggested that a working warp bubble might require a shell of negative energy, equivalent in magnitude to the mass of Jupiter. Not the mass of a starship, not the mass of a mountain or a continent or even a planet. The mass of the largest world in our solar system, the great banded giant that could swallow 1,000 Earths and still have room for more, and this mass would need to be negative, a substance with properties opposite to everything we have ever touched. Let that number settle. Jupiter masses nearly 2 million trillion kilograms. It contains more matter than all the other planets combined. And the early warp drive calculations asked for a bubble of exotic matter with that much negative energy, concentrated into a thin shell around a ship measured in meters. The energy density required would be beyond comprehension, a wall of impossibility so tall that even contemplating it felt more like theology than physics. This was the barrier that made most physicists dismiss the Alcubierre drive as a mathematical curiosity. Yes, the equations worked. Yes, general relativity permitted the distortion. But the price was so steep that it seemed no civilization, no matter how advanced, could ever afford to pay it. The warp drive was possible in principle and impossible in practice, a loophole that led to a locked door. And then the refinements began. Researchers returned to the equations with fresh eyes. They varied the shape of the bubble, they adjusted the thickness of the walls, they explored oscillating configurations, where the warped region pulsed rather than remaining static. And slowly the numbers began to fall. A physicist named Chris van den Broek showed that by adjusting the geometry, shrinking the surface area of the warp bubble relative to its internal volume, the energy requirement could be reduced. Instead of Jupiter, perhaps you needed only a small planet's worth. Still beyond reach, still demanding exotic matter we had never seen, but no longer quite so absurd. Then came Harold White, working at NASA, who proposed that a thicker, more gradually varying warp field might reduce the requirements still further. His calculation suggested that the negative energy might be brought down to something on the order of hundreds of kilograms, not planets, not moons, something that, while still demanding the impossible, at least existed on a scale the mind could hold. Imagine that for a moment. The journey from Jupiter mass to hundreds of kilograms is a reduction of roughly 30 orders of magnitude. It is as if you were told a journey would cost all the money on Earth, and then someone found a receipt that brought the price down to a cup of coffee. The gulf between the two numbers is so vast that it defies intuition, and it happened, not through new physics, but through more careful geometry. Through noticing that the original calculation had made assumptions that were not strictly necessary, had demanded more of the universe than the universe actually required. This is the nature of theoretical progress. Sometimes the breakthrough is not a new discovery, but a better question. Sometimes the wall is not as thick as it first appeared, but even hundreds of kilograms of negative energy remains impossible by our current understanding. We have never produced exotic matter in any quantity. We have never bottled the Casimir effect or harnessed the quantum vacuum in a way that yields usable negative energy. The substance the warp drive demands remains as hypothetical as it was when Alcubierre first wrote his paper. The numbers have fallen, but they have not fallen to zero. The gap between theory and engineering remains a chasm, and there are deeper concerns. Some researchers have questioned whether the optimistic reductions are robust, whether they depend on assumptions that might not hold in a full, self-consistent treatment, whether the geometry tricks that bring down the energy requirements might introduce new pathologies, new instabilities, new reasons why the bubble cannot form or cannot be controlled. The field is not settled. The debates continue in the quiet journals, in the Arxiv preprints, in the small conferences where warp drive enthusiasts gather to share their calculations. There is also the question of how you would ever build such a thing, even if the energy requirements became manageable. A warp bubble is not a device you assemble in a factory. It is a shape cut into space-time itself, a region where the metric of the universe deviates from its ordinary flatness. Creating it would require generating and precisely shaping fields of exotic matter, holding them in configurations of unimaginable precision, and doing so while a starship sits at the center waiting to be carried. We do not know how to do any of this. We do not even know in principle how you would start. The physics is clear about what shape space-time would need to take. It is silent about how you would persuade space-time to take that shape. It is like having a blueprint for a cathedral and no quarry from which to cut the stones. And yet the equations remain. The loophole persists, and in the persistence, in the stubbornness of the mathematics, there is something that will not be dismissed. Consider what has happened before. There was a time when the atom was believed to be indivisible, its very name declaring it uncuttable. We cut it. There was a time when the nucleus seemed a stable thing, its energies locked away forever. We unlocked them, for better and for worse. There was a time when gravitational waves were thought forever beyond detection, ripples so faint that no instrument could ever catch them. We caught them with mirrors and lasers and decades of patient engineering. The impossible has a way of becoming possible when enough minds work on it for long enough. This is not a promise, it is not even a prediction. But it is a pattern, a tendency written into the history of physics. What seems forbidden by one generation often becomes routine for the next. The boundaries move, the walls crumble, and sometimes the crumbling reveals not just a door, but an entire landscape beyond, wider than anything that came before. The warp drive researchers know this history. They carry it with them, a quiet flame that keeps them working when the mainstream dismisses their calculations as fantasy. They are not foolish. They understand the odds. They know that most radical ideas fail, that most theoretical possibilities never become practical realities. But they also know that some do, and they have chosen to spend their careers exploring which category the warp drive might fall into. There is a deeper question here, one that touches the philosophy of science itself. What is the value of studying something that may never be achievable? What is the purpose of calculating the properties of a machine that no one alive today, and perhaps no one ever, will build? One answer is that the journey has worth independent of the destination. The mathematics of warp drives has led researchers to new insights about general relativity, about the behavior of exotic matter, about the nature of horizons and causality. Even if faster-than-light travel remains forever impossible, the tools developed in its pursuit may prove useful elsewhere. Science has a way of finding applications no one predicted, of turning apparently useless knowledge into the foundation for something practical. Another answer is simpler. We study what we study because we want to know, because the questions call to us, because the mystery demands exploration, because the human mind cannot look at a closed door without wondering what lies beyond. The warp drive may be forever out of reach, but understanding why it is out of reach, mapping the exact contours of the impossibility, is itself a form of knowledge worth having. And there is always the chance, however small, that the door is not as closed as it appears, that somewhere in the equations there is a loophole within the loophole, a way to generate the exotic matter or sidestep the need for it entirely, a path we have not yet imagined. The history of physics is littered with discoveries that came from unexpected directions, with solutions that arrived from fields no one thought relevant. Quantum mechanics was born from a puzzle about the glow of hot metal. General relativity came from a thought experiment about elevators and light. The next breakthrough, if it comes, may emerge from equally surprising soil. So the work continues. In small offices and quiet laboratories, on chalkboards and computer screens, the calculations proceed. A new geometry here, a refined estimate there, a question about stability, a proposal for how negative energy might be generated, however speculatively. Each paper adds a tile to the mosaic. None of them, alone, will build a warp drive, but together they map the territory, illuminating what is forbidden and what, just possibly, might be allowed. Let us pause here and feel the weight of this situation. We are a species that has walked on the moon, that has sent robots to the outer planets, that has detected the collision of black holes a billion light-years away. And yet the nearest star remains impossibly far. At our current best speeds, it would take tens of thousands of years to reach Alpha Centauri. The galaxy, that great spiral of hundreds of billions of suns, is effectively close to us. We can see it, we can measure it, we can count its stars and trace its arms and watch its ancient light. But we cannot touch it. We are stranded, marooned on a single world around a single star in a universe of uncountable others. The warp drive is the dream of escape, the dream of stepping beyond the prison of distance that evolution designed us to accept. It is the deepest expression of the restlessness that sent us out of Africa, across oceans, into the sky. And like all such dreams, it exists in tension between longing and limitation, between what we wish and what physics allows. For now, the limitations seem to win. The exotic matter remains hypothetical, the energy requirements remain daunting, the engineering remains completely undefined. But the equations also remain stubborn and patient, describing a shape that space-time could in principle take, a configuration that would carry a ship faster than any light could follow. And in that tension, in that unresolved space between impossibility and possibility, the human imagination continues to work. We cannot stop ourselves. We are a species that looks at walls and thinks about doors, that hears the word never and begins to wonder how. That takes the equations of general relativity, meant to describe the gentle curves of planetary orbits and the fierce bending of light around black holes, and asks whether they might also describe a shortcut to the stars. This is who we are. This is what we do. And whether the warp drive ever becomes real or remains forever a mathematical dream, the asking of the question is itself a kind of triumph, a refusal to be small, a declaration that even the vast emptiness between the stars is not enough to contain our curiosity. The calculations continue, the papers accumulate, the bubble floats in the mathematics, waiting, and somewhere perhaps the answer is waiting too. Hidden in an equation not yet written, in a connection not yet made, in a question not yet asked, the stars burn in their silence, patient beyond measure, indifferent to our dreams. But we keep dreaming anyway. It is the one thing we cannot seem to stop. There are those who argue that this pursuit is a distraction, that our resources would be better spent on problems we know how to solve, on technologies that are only years away rather than centuries, on the pressing crises of a warming planet and a fragile civilization. There is merit in this view. The practical challenges facing humanity are immense and immediate. The warp drive, even in the most optimistic scenario, would not help us for generations. But humanity has never been purely practical. We have always poured some portion of our effort into questions that offered no immediate return, into art and philosophy and fundamental science, into the pursuit of understanding for its own sake. This is not a weakness. It is part of what makes us human. The practical and the visionary are not opposed. They are two aspects of the same restless intelligence, the same refusal to accept the world as it is. And sometimes the visionary becomes practical faster than anyone expected. When Maxwell wrote his equations of electromagnetism in the 19th century, no one foresaw radio, television, the internet. When Einstein dreamed about riding a beam of light, no one imagined GPS satellites timing their signals by relativistic corrections. The boundary between pure curiosity and practical application is more porous than it appears. Knowledge flows across it in ways that cannot be predicted. So let the warp drive researchers do their work. Let them calculate the bubble geometries and the energy densities and the horizon behaviors. Let them argue about the meaning of negative energy and the stability of the walls. Even if they are chasing a ghost, even if the destination never comes into reach, the journey itself has value. The tools they develop, the questions they ask, the boundaries they map, all of this becomes part of the great accumulation of human knowledge, available for purposes we cannot yet imagine. And perhaps, just perhaps, one day the ghost will prove to be real. One day a paper will appear, or a discovery will be made, or an experiment will succeed in a way no one anticipated. And the bubble that floats today only in the mathematics will begin its slow journey toward the engineering. The exotic matter will be found or created or circumvented. The energy requirements will fall to something achievable. The shape of space-time will finally bend to our will. That day may never come. The odds are against it. But the possibility, however faint, is real. And as long as it remains real, the work will continue. The calculations will proceed, the dream will persist, because we cannot look at the stars and not wonder how to reach them, because the distances call to us, even as they mock our attempts. Because we are the species that walks toward the horizon, knowing it can never be reached and keeps walking anyway. And perhaps that is the deepest truth about this entire endeavour, not whether it will succeed, but what it reveals about the creatures who pursue it. We are the only beings we know of who look at the absolute laws of the universe and ask quietly, politely, whether there might be a way around them. We are the only minds that can hold in contemplation both the certainty of limitation and the possibility of transcendence. The warp drive, real or imagined, is a mirror, and what it reflects back is something stranger than any exotic matter, more remarkable than any bubble of contracted space. It reflects a species that refuses, on some fundamental level, to accept the boundaries of its existence. Consider what this means. For most of life on Earth, the horizon is simply the edge of perception. A bird does not wonder what lies beyond the mountains it has never crossed. A fish does not contemplate the nature of the water it swims through. But we do. We have always done this. We stand on the shore and ask what lies beyond the sea. We climb the mountain and ask what lies beyond the sky. We map the stars and ask what lies beyond the light we can see. This is not arrogance. It is something closer to compulsion. A need written into the architecture of our consciousness. We are the species that builds boats to cross water, then ships to cross oceans, then rockets to cross the void. And when the void proves too vast for any rocket we can build, we begin to ask whether perhaps the void itself could be convinced to carry us. The mathematics of the warp drive, whatever its ultimate fate, is a continuation of this ancient impulse. It is Polynesian wayfinders watching the stars and the swells, reading a language of navigation that others could not even perceive. It is Magellan's crew sailing into the unknown, uncertain whether the world curved back on itself or simply ended in a waterfall of darkness. It is the Wright brothers at Kitty Hawk, their fragile machine lifting for 12 seconds into a wind that had no memory of human flight. Each time the challenge seemed impossible until it was achieved. Each time the horizon retreated, revealing new horizons beyond. And each time there were voices arguing that the attempt was folly, that resources should be devoted to more practical concerns, that the dreamers should content themselves with the world as it was. Those voices are not wrong to counsel caution. They are not wrong to point to the immense challenges of the present, but they are describing only half of the human equation. The other half is the restlessness that will not be stilled, the itch at the back of the mind that asks always, what if? This is not a flaw to be corrected. It is a feature of our consciousness, perhaps the feature that matters most. Strip away this quality, and we are no longer ourselves. We become something smaller, something more sensible, something that would never have left the African savannah in the first place. So the calculation continues, not because it is practical, not because it promises any near-term return, but because we are built to calculate things like this, because the question, once asked, cannot be unasked, because somewhere in the mathematics there is a shape that looks like a bubble, and inside that bubble there is a stillness, and around that stillness space-time itself does the impossible work of carrying us toward destinations we cannot otherwise reach. Let me try to give you one more way to feel the scale of what this would mean. Forget the numbers for a moment. Forget the energy requirements and the exotic matter and the theoretical objections. Think instead about what it would be like to actually achieve it. To stand at the window of a ship wrapped in its bubble of warped space and watch the stars begin to move. Not the slow drift of normal travel, where even at enormous speeds the stars remain fixed points for centuries, but actual motion, stars sliding past, constellations distorting and reforming, the galaxy itself becoming a landscape you move through, rather than a static backdrop impossibly far away. This has never happened. In all the billions of years since the first galaxies formed, in all the uncountable number of stars that have burned and died, there is no evidence that anything has ever travelled between them faster than light. The cosmos has existed in a state of profound isolation, each star separated from its neighbours by gulfs of space that take centuries, millennia, millions of years to cross at any velocity physics allows. If the warp drive were possible, if it were actually achievable, It would change the character of the universe itself. Not in any physical sense, but in what the universe means. The isolation would end. The stars would become for the first time accessible, not in theory, not in imagination, but in practice. You could go there. You could stand on the surface of a planet orbiting a different sun and look up at the sky and recognize none of the constellations, and know that every photon striking your eyes had travelled from sources your own sun could never see. This is why the dream persists despite the obstacles. This is why the papers continue to be written, the calculations continue to be refined, the objections continue to be raised and addressed, because the prize is not merely a faster way to travel. The prize is a transformation in the relationship between conscious life and the cosmos that contains it. The prize is escape from a prison we have only recently discovered we inhabit, the prison of distance, of time, of the vast indifferent gulfs that separate everything from everything else. The warp drive, if it were real, would not just be a technology, it would be a liberation. But let us not lose ourselves entirely in the dream. Let us come back, as we must always come back, to the mathematics, to the careful, patient, rigorous work of people who spend their lives trying to understand what the equations actually permit. Because the mathematics is where the dream meets reality. The mathematics is where we discover whether the bubble can truly exist, whether the energy can truly be generated, whether the travellers inside can truly survive. And the mathematics, as we have seen, is complicated. There are solutions that seem to work and then fail under closer examination. There are loopholes that open and then close. There are requirements that can be reduced but perhaps never eliminated. The picture shifts with every new paper, every new insight, every new objection and response. What is the current state of the field? It is difficult to summarize because the field is so small, so speculative, so far from mainstream physics that it barely exists as a coherent community. There are perhaps a few dozen researchers worldwide who work seriously on warp drive theory, and even among these few there is no consensus on whether the goal is achievable or absurd. Some believe that the recent developments, the reduction of energy requirements, the exploration of alternative geometries, the possibility of physical effects that might mimic aspects of warp behaviour, represent genuine progress toward a more modest but still useful form of faster-than-light travel. Others believe that the fundamental obstacles have not been touched, that the exotic matter requirement cannot be circumvented no matter how the geometry is modified, that the entire enterprise is a beautiful mathematical exercise with no connection to physical reality. Both positions are defensible. Both are held by intelligent, well-informed people who have spent years studying these questions. And this uncertainty is itself significant. If the warp drive were clearly impossible, if some theorem could be proven showing that no configuration of matter and energy could ever produce the required warping of space-time, then the field would close and the researchers would move on. But no such theorem exists. The door remains open, however narrowly, and as long as the door remains open, there will be minds pushing against it, trying to see what lies on the other side. There is something else worth noting here. The very act of exploring these questions, even if they lead nowhere, expands our understanding of the universe. The study of warp drive geometries has led to new insights into the nature of space-time, into the behaviour of horizons and causal structures, into the relationship between geometry and energy that lies at the heart of general relativity. These insights have value independent of whether a warp drive is ever built. They become part of the accumulating knowledge of our species, available for applications we cannot foresee. The history of science is full of such unexpected connections. Research conducted for one purpose turns out to be essential for something entirely different. The tools developed to solve one problem become the foundation for solving others. The questions asked in one generation become the answers needed by the next. So the warp drive researchers are not merely chasing a dream, they are also doing physics. They are probing the structure of the theory, testing its limits, exploring the strange geometries that the equations permit. They are contributing to our collective understanding of reality, even if the specific goal that motivates them never comes to fruition. This is how science works. It is not a straight line from question to answer. It is a vast network of intersecting paths, some leading to dead ends, some opening into unexpected vistas, all contributing to the gradual expansion of what we know. The warp drive may be a dead end. It may be a vista. We cannot know until we follow the path. And what of the practical considerations? What would it actually take to build such a thing if the theoretical obstacles could be overcome? Here the speculation becomes even more uncertain, because we are so far from having a workable theory that engineering considerations are almost meaningless. But let us imagine for a moment that the physics were solved, that someone discovered a form of energy that met the requirements, or a geometry that needed no exotic matter, or some other solution we cannot yet conceive. What then? The engineering would be beyond anything we have ever attempted. The precision required would make our most delicate instruments look crude by comparison. The energies involved, even in the most optimistic scenarios, would exceed anything we can currently generate. The control systems would need to manipulate space-time itself with an accuracy that has no parallel in any technology we possess. The ship would not be a vehicle in any conventional sense. It would be a collaboration between matter and geometry, a sculpture in the shape of space-time, a device that functions by convincing the universe to rearrange itself around a tiny bubble of stillness. How long would such a development take? Centuries, at minimum. Perhaps millennia. Perhaps never. The gap between our current capabilities and what the warp drive would require is so vast that no timeline makes sense. We're not talking about incremental progress, about slightly better engines and slightly more efficient fuel. We're talking about a revolution in our understanding of physics itself, followed by a revolution in our ability to manipulate the fundamental structure of reality. These are not tasks that can be scheduled. They happen when they happen, if they happen at all. The warp drive, if it comes, will come on its own schedule. All we can do is continue the work and see where it leads. But there is one more piece to this story, one more consideration that rarely appears in the technical papers, but haunts the edges of the dream. What would we do with a warp drive if we had one? What would faster-than-light travel mean for a species like ours? Consider the implications. The galaxy contains hundreds of billions of stars. Many of them host planets. Some of those planets, statistics suggest, must harbour life, perhaps even intelligent life. Perhaps civilizations far older and more advanced than our own. With a warp drive, we could go looking for them. We could send probes to nearby systems, then to more distant ones, then to the spiral arms and the core and the halo of old stars that surrounds everything. We could answer, finally, the question that has haunted us since we first understood what the stars were. Are we alone? The answer might be yes. The galaxy might be empty, silent, devoid of anything like us. This would be its own kind of answer, its own kind of revelation. It would mean that consciousness, that awareness, that the capacity to ask questions about the universe is rare beyond all imagining. It would mean that we are precious, fragile, the only minds in a desert of matter and energy. It would place upon us a burden we can barely conceive, the responsibility of being the sole witnesses, the only place where the universe knows itself. Or the answer might be no. There might be others out there. Civilizations that arose billions of years before us, that have had time to spread across the stars, that have technologies and understandings beyond anything we can imagine. Meeting them would change everything, not just our technology, not just our science, but our entire sense of ourselves and our place in creation. We would become members of a community rather than isolated individuals. We would have context, we would have comparison. We would know, finally, whether the path we have walked is the only path or one among many. These possibilities are so vast, so transformative, that they almost defy contemplation. And yet they are precisely what a working warp drive would open up. The technology itself is secondary. What matters is the reach it would provide, the ability to cross the gulfs that currently make us prisoners of our own solar system. The warp drive is not really about physics. It is about contact, about possibility, about discovering what else exists in this enormous, mostly empty, almost entirely unexplored universe. Perhaps this is why the dream will not die. Not because the physics is encouraging, it is not. Not because the engineering is feasible, it is far from it. But because what lies on the other side of that wall is too significant to ignore. The chance, however slim, of reaching the stars is worth pursuing even if the odds of success are vanishingly small. Because the alternative is to sit here, in our one solar system, on our one fragile planet, knowing that the cosmos spreads out in every direction and we can barely touch the nearest edges of it. That alternative is unbearable to a species like ours, so we keep working, we keep dreaming, we keep asking whether the bubble might be real. The mathematics floats in its realm of abstraction, neither promising nor forbidding. The exotic matter remains hypothetical, a placeholder for something we have not yet found. The energy requirements have fallen but not far enough. The theoretical objections have been addressed but not resolved. Everything about this endeavour hangs in suspension, neither dead nor alive, waiting for some development we cannot predict. And in the meantime, the stars continue their ancient burning. Patient, indifferent, impossibly far away, but not perhaps forever out of reach. This is the thought that sustains the work, the knowledge that impossibility is sometimes just ignorance by another name, that the walls we encounter are sometimes made of our own assumptions, that the universe, strange as it is, has repeatedly turned out to be stranger than we expected, with hidden doors where we saw only solid barriers. The warp drive may be such a door, or it may be a beautiful illusion, a place where the mathematics leads us on and reality refuses to follow. We do not know yet. We cannot know until we keep working. And so the work continues. The papers appear, the calculations deepen. The bubble remains in its mathematics, waiting for someone to discover whether it can ever become real. And there it waits. A geometry written in tensors and curvature, a shape that might carry us to the stars or might remain forever in the realm of elegant impossibility. The bubble floats in its equations like a ship in a bottle, perfect and still, while we press our faces to the glass and wonder if there is any way to reach inside. But perhaps we have been asking the wrong question all along. We have asked whether the warp drive is possible, whether the physics permits it, whether the exotic matter exists, whether the energy can be gathered. These are the questions of engineers, of builders, of people who want to know whether the bridge can hold weight before they step onto it. They are good questions, necessary questions, but they are not the only questions. There is another way to look at this strange chapter in human thought, not as a problem to be solved, but as a mirror held up to ourselves. What does it say about us that we dream this dream at all? What does it reveal that we cannot let it go? Consider the sheer improbability of the creature that imagines warp bubbles. A small primate on a medium-sized planet around an ordinary star in an unremarkable galaxy, in a universe so vast that the distance to our nearest stellar neighbour already strains comprehension. This creature has existed for a few 100,000 years. It developed language perhaps 100,000 years ago, writing a few thousand, mathematics as we know it a few centuries, quantum mechanics and general relativity barely a century. And already, within this blink of cosmic time, it has begun to ask whether the very fabric of space might be bent to carry it to the stars. There is something almost absurd about this. A mayfly dreaming of hibernation, a bacterium contemplating cathedral architecture. The gulf between what we are and what we dream of doing is so immense that it should be comical, and yet somehow it is not comical. Somehow it feels exactly right that we should dream this way, as if the dreaming itself were the point, as if the reaching were more important than the grasping. Let that thought settle for a moment. We are not the first species to move. Life has been spreading across this planet for nearly 4 billion years, filling every niche, colonizing every environment, pushing into the deep ocean and the upper atmosphere and the frozen poles and the boiling vents. Movement is written into the grammar of biology. Expansion is the oldest story life knows how to tell. And now, after all those billions of years of spreading across a single world, life has produced a form that looks up at the night sky and asks whether the spreading might continue. The warp drive, in this light, is not really a technology. It is a question. The question life itself has been asking since the first replicating molecule divided and produced a copy slightly different from itself. The question is simple. What else is possible? What other shapes might existence take? What lies beyond the edge of the map? We do not know whether we will ever build a working warp bubble. The honest answer, the answer that respects everything we have learned, is that we probably will not. The obstacles are too severe, the exotic matter too hypothetical, the energy requirements too crushing, the theoretical objections too sharp. If you forced a physicist to bet, most would bet against it. Some would bet against it heavily. The smart money, as they say, is on impossibility. But the smart money has been wrong before. A century ago, the smart money would have bet against heavier-than-air flight. Not because the physics was impossible, but because the engineering seemed insurmountable. The power-to-weight ratios of existing engines were too poor. The understanding of aerodynamics was too primitive. The materials were too heavy and too weak. Serious scientists wrote serious papers explaining why sustained controlled flight would never work. And then two brothers from Ohio, with no formal engineering training, built a working airplane in a bicycle shop. Half a century ago, the smart money would have bet against placing men on the moon within a decade. The rockets did not exist. The computers did not exist. The materials did not exist. The life support systems did not exist. The entire endeavour required inventing dozens of technologies simultaneously, any one of which could have proved intractable. And yet, 8 years after Kennedy's speech, Armstrong stepped onto the regolith. This is not to say that the warp drive will follow the same pattern. Flight and moon landings were difficult but not impossible according to known physics. The warp drive may be genuinely impossible, blocked not by engineering challenges but by fundamental laws we do not yet fully understand. The analogy is imperfect, perhaps even misleading. But the analogy is not the point. The point is that we do not know what we do not know. The future is not a straight line extrapolation from the present. It branches and turns and sometimes folds back on itself. Technologies emerge that nobody predicted. Discoveries arrive that reshape entire fields overnight. A century ago, no one imagined smartphones. Half a century ago, no one imagined the internet as it now exists. A quarter century ago, no one imagined that gravitational waves from merging black holes would be detected by lasers bouncing in 4-kilometre tunnels. The future has a way of surprising us. Perhaps the warp drive will never be built. Perhaps it will remain forever in its mathematics, a beautiful castle in the air that no one can ever inhabit. This is the most likely outcome. Anyone who tells you otherwise is selling something. But perhaps, that word is enough. Perhaps we will discover something about quantum gravity that changes everything. Perhaps some form of exotic matter will turn out to exist. Perhaps the energy requirements will fall by factors we cannot yet imagine. Perhaps some other approach will emerge, something that bypasses the difficulties entirely, that solves the problem from a direction no one has yet thought to look. We cannot rule it out. The universe has repeatedly shown itself to be stranger than we expected, with resources and possibilities we never anticipated. The history of physics is a history of discovering that reality permits more than we thought possible. Atoms were supposed to be indivisible. Space and time were supposed to be absolute. The universe was supposed to be static and eternal. The vacuum was supposed to be empty. Each of these assumptions turned out to be wrong in ways that open new doors. The warp drive may be another such door, or it may be a wall that can never be breached. We will not know until we look more closely, until we probe more deeply, until we test the theories against the universe itself. And that work is happening, slowly, cautiously, without the glamour and funding of a moon race, but happening nonetheless. In laboratories around the world, physicists continue to study the Casimir effect, pushing the precision of the measurements, looking for any sign that the vacuum holds more surprises. In theoretical departments, researchers continue to chip away at the equations, looking for loopholes within loopholes, places where the energy might fall further or the instabilities might be tamed. In simulation centres, computers model the behaviour of warped space-time, revealing subtleties that pencil and paper calculations might miss. None of this work promises success. Most of it will probably lead nowhere. That is how fundamental research works. You plant 1,000 seeds knowing that most will not sprout. But you plant them anyway, because the ones that do sprout sometimes change everything. And while the physicists work, the rest of us wait. We look up at the stars on clear nights and feel the old ache, the longing that has no name but that every human recognises. The stars are there, burning in their billions, surrounded by planets we can now photograph, worlds we can now analyse, places that might harbour life or might be waiting for life to arrive. They are there and we are here, and the gulf between us is almost too vast to hold in a single thought. The Alcubierre drive, if it ever works, would close that gulf. Not instantly, not easily, but meaningfully. It would turn the stars from distant points of light into actual destinations. It would transform our cosmic prison into a neighbourhood. It would give us room to grow, to spread, to become something more than a single species on a single world, fragile and alone. This is the dream. Not the engineering, not the exotic matter, not the negative energy density. The dream is the reaching, The dream is the possibility of contact with whatever else might exist out there. The dream is becoming citizens of a larger universe, and dreams matter. They matter because they shape what we attempt. They matter because they tell us who we are trying to be. They matter because the stories we tell ourselves about the future influence the choices we make in the present. A species that dreams of the stars is different from one that does not. Not necessarily better, but different in ways that have consequences. The warp drive dream keeps certain questions alive. It forces us to confront the limits of our knowledge and to ask whether those limits are permanent or temporary. It reminds us that the universe operates according to laws we did not write and do not fully understand, laws that might contain possibilities we have not yet imagined. It keeps us humble and ambitious at the same time, aware of how much we do not know, but unwilling to assume that our ignorance is final. This is no small thing. In a world full of immediate crises, full of problems that demand attention right now, it might seem foolish to spend time and resources on something as speculative as faster-than-light travel. There are diseases to cure, climates to stabilize, billions of people whose basic needs are not yet met. What business do we have dreaming of the stars when we have not yet learned to take care of our own planet? The question is fair, but it contains a false assumption. It assumes that we must choose, that resources spent on one thing cannot be spent on another, that attention is a finite pie that must be carefully divided. In some narrow budgetary sense, this is true, but in the larger sense of what a civilization can hold in its mind, it is not true at all. We are capable of caring about many things at once. We can feed the hungry and also wonder about the stars. We can stabilize the climate and also dream of warp bubbles. The one does not preclude the other. If anything, they reinforce each other. A civilization that has solved its terrestrial problems will need somewhere to direct its restless energy. And a civilization that has no dreams beyond its own survival will have little reason to solve those problems in the first place. The warp drive is a horizon. It is something to walk toward even if we never arrive, and horizons matter. They give direction, they give meaning, they keep us moving forward instead of simply circling in place. Rest with that for a moment. Here, then, is where we stand. A bubble of mathematics that might someday become real. A loophole in the laws of reality that remains neither closed nor open. A dream that will not die because what it promises is too significant to abandon, even when the odds seem impossibly long. The exotic matter has not been found, the energy requirements have not been met, the instabilities have not been resolved. The horizon problem, the tidal forces, the causal paradoxes, all remain to be addressed. Any honest accounting must admit that the obstacles are severe, perhaps insurmountable. The warp drive may never be built. It may remain forever in its equations, a tantalizing glimpse of what physics might have permitted if only the universe had been slightly more generous. And yet, the papers keep appearing, the physicists keep calculating, the dreamers keep dreaming. Something about this idea refuses to let go, refuses to be filed away and forgotten. It persists, like a melody you cannot shake, like a question that demands an answer even when no answer seems forthcoming. Perhaps this persistence is irrational. Perhaps we should be more grown up about it, should acknowledge the likely impossibility, and move on to more tractable problems. That would be the sensible thing to do. The smart money again would advise against continuing to chase this particular rainbow. But we're not entirely creatures of the smart money. We're also creatures who painted bison on cave walls before we had anything practical to do with the images. We are creatures who built cathedrals that took centuries to complete, knowing we would never live to see the finished work. We are creatures who sent Voyager carrying a golden record, just in case someone out there might be listening. We do impractical things. We chase rainbows. It is part of what makes us who we are. The warp drive is one such rainbow. Not the only one, not the most important one, but a rainbow nonetheless. A streak of colour against an otherwise dark sky. A reminder that the universe may hold possibilities beyond our current sight. And so, the work continues. In quiet rooms and on glowing screens, in the margins of textbooks and the imaginations of students who have not yet learned what is supposed to be impossible. The bubble drifts in its mathematics, neither promising nor forbidding. The stars burn on in their ancient indifference, impossibly far, impossibly bright. And somewhere between the mathematics and the stars the question hangs suspended. Can we get there? We do not know. We cannot know, not yet. Perhaps not ever. The answer may lie a decade in the future, or a century, or 1,000 years, or nowhere at all. It may come suddenly, in a flash of insight that rewrites everything we thought we understood, or it may come gradually, through a long accumulation of small advances, each one bringing the dream a little closer to reality, or it may never come. The door may be locked, the wall unbreachable, the dream destined to remain forever a dream. But we will keep asking, that much is certain. As long as we are the kind of creature we are, as long as we look up at the stars and feel that ancient ache, we will keep asking. Because the asking itself is part of what makes us human. Because the reaching, even when we do not grasp, is how we grow. Because the dream, even if it never becomes real, shapes us into something larger than we would otherwise be. The universe is under no obligation to make itself convenient for human travel. It did not design itself with our dreams in mind. The distances are vast because they are vast, not to teach us a lesson or to test our resolve. The laws of physics are what they are, indifferent to our hopes and plans, but those same laws, those same vast distances, also produced us. They produced a form of matter that can ask questions about its own existence. They produced curiosity and imagination, and the willingness to attempt things that seem impossible. The universe made the prison, but it also made the prisoners who dream of escape. Maybe that is enough. Maybe the dreaming itself is the escape. Maybe the journey toward the stars, even if we never complete it, is what matters most. The reaching, the trying, the refusal to accept that the cage is final. Out there, beyond the blue shell of our atmosphere, beyond the familiar warmth of our sun, the cosmos stretches away in all directions. Galaxies by the hundreds of billions, stars beyond counting, planets we're only beginning to glimpse, possibilities we cannot imagine, all of it waiting, patient, silent, for whoever or whatever might come looking. We may never build a warp drive. We may be confined forever to this one small system, this one small world. But we will have looked up. We will have asked the question. We will have refused to believe that the walls around us are permanent even if we never find a door. And that refusal, that persistent dreaming, is its own kind of answer. The bubble remains in its mathematics. The stars continue their ancient burning. The distance between them and us is measured in years of light, in journeys so long that generations would pass before arrival. Nothing has changed, and yet everything has changed. Because now we know that the law of light is not quite what we thought it was. Because now we know that space itself might be bent and stretched and carried. Because now we carry in our minds the shape of a possibility, a geometry that might someday become a vessel. We do not know where that geometry will lead. We do not know if it leads anywhere at all, but we have drawn the map. We have named the destination, and we have begun, in our slow and uncertain way, to walk toward it. The stars are waiting. They have always been waiting, and perhaps in some future we cannot yet see, someone will finally arrive to meet them,